Hello, welcome to my conference talk today. My name is Gongrui Zhang, or you can call me Henry Zhang. So this is a project I did with Polygence with Siddharth as my mentor about 1 month ago, and it's about electroreduction electrocatalysts in proton exchange membrane fuel cells. So I'm a chemistry student, and I really wanted to do a chemistry research project like this. Despite it's a literature review, it adds to my academic knowledge and self-experiences as writing research papers for school. I'm currently in Sydney in Australia, so I should be delivering this online due to the time zone differences. But regardless, I wish you guys enjoy this conference talk that I'm gonna go through today. So today we're gonna talk about the oxygen reduction electrocatalysts in proton exchange membrane fuel cells. So why do we need to address this problem? First, you need to think about the global status that we're looking at right now. Currently, there's an average increase of 0.32 Fahrenheit or 0.12 degrees Celsius per decade increase since 1981. And from 1990 to 2015, the net greenhouse gas emissions from human activities increased by 43%, with carbon dioxide accounting for about 3/4 of the total emissions, increasing by 51%. From the graph to the right, you can definitely see that carbon dioxide contributes a lot of the greenhouse gas emissions. So it is our best interest to try to stop or control the output of the greenhouse gases. And that's why we're here today introducing our topic. So what we would go through today. So the overview of today's symposium will first cover the background information, what are fuel cells, and more like what are electrocatalysts. And second is what is the criteria for a good electrocatalyst, and we'll be covering two characteristics involving kinetics and the durability of the catalysts. And the third is a comparison of electrocatalysts. We'll be comparing mostly PGM catalysts, which is platinum group metal catalysts, and non-platinum group metal catalysts, which is non-PGM catalysts. And this will be compared in three aspects that includes the efficiency, the durability, and the cost and scarcity of the catalyst. Four is the future potential that we could improve to improve this scenario that we have, and then we're gonna end off with a conclusion. So, what is a fuel cell? For those of you guys don't know, a fuel cell is essentially like a battery. It consists of two electrodes, the cathode and the anode, and an electrolyte in the middle that transport the ions, as you can see from your fuel cell diagram to the right. The hydrogen fuel is fed through the anode, and then it will decompose into electrons going through the external circuit, and then form water as a byproduct on the cathode and released. So this will go through the redox reactions, which is key. From the redox reactions, you can see that hydrogen ions is first break down into hydrogen ions and two electrocatalysts that follows the external circuit that generates our electricity. And same with oxygen from the cathode. It will then form with the hydrogen ions from the anode to form water as a byproduct. During this process, it's obvious that no carbon dioxide or any greenhouse gases emission as a byproduct, which means that this is a really good and energy saving and environment friendly way to generate electricity. So yeah, the redox reaction is basically what we need to know for fuel cells. It is a key for energy conversion between a fuel cell. O2 gas is reduced to water and releases energy that contributes to the overall electricity generation, leading this to the perfect energy, clean energy resource that we want. So now what is the role of electrocatalysts in this place? So first, as we know, catalyst lowers the activation energy of reactions. And now electrocatalyst lowers the activation energy of the redox reactions we just mentioned. And also it determines the magnitude and the current between anode and cathode, which is important as the more efficient your redox reactions is, that means you produce your energy and electricity in a faster rate. And with more electricity generated, it definitely contributes more to being more environmentally friendly and maximize it for us humans. So now what's the criteria for the electrocatalysts? The two things I will go through is kinetics and durability. The kinetics by how the condition of a process will impact the rate of oxidation and reduction reaction, and durability, which describes how long the electrocatalyst can sustain with the whole reaction. By considering the two factors, it will show the most cost effectiveness catalysts and also which catalysts can fulfill better jobs. So before getting to the kinetics is that what is oxygen reduction reaction? So it's when a molecular oxygen bound onto the catalyst surface, lowering the energy barrier of the oxygen bonds. These molecules will then react with the 4 protons and electrons to generate oxygen ions. These ions then travel through the anode that releases electricity and water as byproducts. So oxygen reduction reaction is underneath the redox reactions we just mentioned. And this is another main process reaction that will be taking into place as it determines the electricity and water that releases as a byproduct. Seen from the table down below, it describes how in acidic aqueous solutions, a reaction process that occurs. And for every oxygen and hydrogen ion bonded, it will generate water on the other side as a react or product of the reactions, which means water is successfully generated, and we want that because it reduces our greenhouse gas emissions, which addresses our global problem. So, how do you analyze the kinetics? The kinetics is analyzed by a curve we call polarization curves. So it is a graphical representation that measures the kinetics of a reaction within the fuel cell, determined by P equals IV, so power equals your current times voltage, like they say in physics. So, however, with polarization curves, it's say in the equilibrium potential or the maximum voltage, it occurs at zero current. So when you start off, it occurs at zero current, and which is approximately 1.229 volts from your graph to the right, which is the figure I've drawn personally. So, and to analyze it, the further you're away from your equilibrium potential, the more inefficiency your catalyst is used, which uses the mass-specific activity they will measure, which is MSA, which we'll reference later on. So from the graph, it's obvious that the red catalyst, the line indicated by the red color, has worse kinetics than the blue line because it's further away from equilibrium potential, if it helps. So now, what is durability and how is it affected? So durability is mostly affected by the degradation of the electrochemically active surface area on the catalyst. If your catalyst surface area gets degraded, it means that less surface area will be used for reactions. So this is in 3 cases mostly dependent on, which is firstly the platinum particle agglomeration and growth. So we're focusing on platinum catalyst now because it is a main focus of catalyst that's used in fuel cells. And then second is platinum loss and migration, the platinum ions getting lost in the process when you continue to use it, and then the contamination of active sites. So how do you measure it? Looking at the left of the slides, the degradation mechanism on the right is simulated through stress testing, which is mentioned above in the 2 figures above. So it's essentially simulating the catalysts at different time intervals, keep on simulating them, and examining the change on the MSA of the polarization curve, which we just talked about, that measures the kinetic. From the graph, you'll see in different hours, the graph changes as they slowly decay from the equilibrium potential, meaning that the kinetics is decreasing. So now I'm going to compare the electrocatalyst, the efficiency, the durability, and the cost of scarcity. So what is efficiency? What determines the efficiency? The efficiency with mostly measured by its d-band structure, which because most metal catalysts possess a d-band structure that gives them a high d-state energy, it gives them a greater catalytic reactivity. And also, the reason why metal catalysts are more efficient is because they can be more easily engineered into smaller nanoparticles. And with smaller nanoparticles, it means that the ESA, the electrochemically active surface area for reactions, is greater, which leads to higher rate of reactions. And also, why is durability agreed in such a case? Because platinum group metal catalysts, so PGM catalysts, have better stress testing results. This is because there's stronger metal support interactions between the metal ions, and also the higher relative inertness that metals possesses and non-metals doesn't. So another factors that we take into account is the cost and scarcity of the catalyst that really differs PGM catalysts from non-PGM catalysts. So from the table to your left, it's pretty obvious that iron, copper, and lead, they are significantly higher than non-PGM catalysts. When you compare to things like that, like platinum, palladium, and rhodium, which are our PGM catalysts. Remember, PGM catalyst is not metal only. They are the things like platinum catalysts, like palladium catalysts, like rhodium catalysts, unlike metal, copper, and lead, which you see every day. And also the scarcity of non-PGM catalysts is higher than PGM catalysts, which means that more people were likely to choose them because due to their more cost effectiveness. So, what are some future potentials that could benefit us from this case? So, more effective investigation should focus on the MEA testings as it provides more insightful results for catalysts operating through fuel cells. All the graphs I demonstrated to you guys today are MEA tests instead of rotating electric disk tests because it demonstrates a better accurate result. However, the MEA tests were really hard to find, so therefore, if we really focus on making more of these tests, it would definitely benefit the analyze of electrocatalysts. And also to investigate NFDF structured catalysts as they provide no carbon support, enhancing stability. I possibly said, the fuel cells right now, the catalysts have a porous structure. This is because of their carbon support. But in SDF structured catalysts, they have no carbon support, which reduces this instability that carbon support brings, which includes stability and durability in the near future. So, in conclusion, the most two deciding factors between PGM catalysts and non-PGM catalysts is that if you want to have a more efficiency and more effective reaction, you will use PGM catalysts, as we just described, multiple reasons. However, if you are an industry who just wants some cost-effective catalysts that can sustain your daily reactions and daily generation of electricity through fuel cells, then non-PGM catalyst is your way to go due to its cost effectiveness, it's cheap, and it has a better scarcity. Thank you for listening today, and I wish you the best of day, and I hope you enjoyed this conference talk. Thank you.